Hi. In the last video I was taking this bike model and we were looking at creating a geared mechanism on the crank, and I said that we want to take it down a slope and see what sort of things happen to it. So what I've done with this one is that I've first created, using mechanical systems design, basically as an enhancement of the assembly design, but what I've done now is I've actually activated mechanical systems experience, and it creates a simulation model here which we're able to then create scenarios inside and select the results from. And it actually creates, and we saw this workspace as we got it before. So what I've done with it, I've actually created a ramp for the bike to go down, drop off the end of there, and try to get up to the end of this one. So that was the first thing, and that ramp needed to be fixed in space. What you also see is that I've created a spring between the elements of the damper, and we've connected the wheels to the ramp. So first of all, let's look at what we did with this connection here. In this contact we have the two wheels in contact with a group which is just on the floor. And the trick with that is that apart from setting the friction properties and various other things that we can do there, we specify the mesh, compute the mesh, and it says OK, and once we've got a green tick in there, then the contacts there will be correct. Just give that a whiz. That's still OK. So that's the first thing, connecting the tyres to the roadway, and I've deliberately set the bike about half a metre off the track, so the first piece will actually drop it onto this track here. And then what I've done is I've actually set a planar offset to make sure that the vehicle actually stays in the middle of the track, and I've put this offset to make sure it stays upright. And then what else have I done? We've got a spring in there which I'll come to in a sec, but one of the things that's important is that it won't do these simulations unless there is some inertia set based upon the information in the model. Now if we go to weight definition, we get this BI Essentials pops up here, and sometimes it comes up showing you exactly what's missing, and for some reason or other it doesn't seem to work in this particular case. But the computed weight of this whole assembly, it seems heavy. It's it's over a ton. The reason for that is that I've even computed a weight on the ramp, which really is irrelevant. So the bike frame its computed weight is 1.5 kilos. So if we select all of these, then we can see what masses are actually applied here. Now if I select, for instance, this wheel, it's got a computed mass of 0.83, but I've had to cheat a little bit. But if you click on that hyperlink, you don't really get sufficient of this information, and what will happen is the system will report back that it can't compute the inertia on some of the parts. So you really need to actually make sure that it's actually computing from the definition of the model properties. Now what I've done with this particular one, I'll be honest, I've put it in as rubber, but I've actually cheated by changing the density of the material to get that down to the right weight. Otherwise it's, you know, a little bit heavy. The model isn't particularly well defined in terms of applying the weights, but that's important that you do that. And then in the engineering connections there. If we look at the spring that I've produced, the spring is actually connected from here, but let's have a look at what I've done. And the supports, it needs to be a point. So what I've done with this, I've actually created or unhidden the axis system so I can pick the origin, and then I've messed about with the elasticity and the damping, and you can play with that yourselves, and the reference length. First of all, I cleared that, and it actually computes what the reference length is between those 2 points there. So, but it does need that to be. It also says in the instructions that you will get options to tick in which direction to put the force, but it doesn't seem to offer me anything other than the function on X in both the damping and the elasticity. And there's a bit of science involved with working out the meaning of these units in each case. So I'm going to leave that for you to investigate. So the spring is associated with that. Let's give that a whiz. And that's about it really as far as that's concerned, just these 3 new things in here. And then by double clicking on the scenario, we can change the workbench to experience, and in here we have a dynamic scenario which I've created from here. Now a dynamic scenario will apply forces and various other things to it. So one of the things you need to excite it with is the gravity, which we can get from here, and because of the way this has been modelled, it's been modelled with Y up, so the normal gravity actually defaults to Z, so we'd have to change it to make sure it came down on the Y. The other thing is that it doesn't actually show you the arrow when you're doing this edit, which is a bit strange, but that's the gravity which you need at the very least. And so I've already created this scenario, and you can see that it's got a little red symbol on it there, which means it needs to be updated because I've been messing about with the constraints. If we double click it, you can see that at the moment I've created a heavy rider and the power on the rider, but the gravity and also some probes in there have been put in. Let's put these things back in there and we'll show you how I actually did it. Set the parameters to about 2.5 seconds total time. Most of this other things is okay, and if we replay that we can see what happens. Now in here we can either compute and generate the results, or we can just preview the scenario, and let's just preview it. Bike bounces down the track. Bear in mind that's only gone half a second. That hasn't gone a second yet. That's a second. Drops off the end of the track, bounces around a little bit, and it should stop around about the end of the track. And I've adjusted the length of the simulation to make sure it doesn't actually drop off the end of the track, which it might just do. Whoa, off it goes. 2.5 seconds is probably a bit too much. But so the other thing that we did there is that I excited it with a force, and the force I put on it is actually being placed on the frame. So the support is the frame, the origin is in fact the origin of the axis of that, and the direction is in the Y, and I'm putting a 900 Newton force in negative Y. That represents a 90 kilo rider who's quite heavy, which is why I've called him Heavy Rider. And when we've created that, it automatically gets placed into the scenario, or as you double click into that, we can actually remove or place that rider into being there. And the second thing I did was I applied a torque, and the torque is applied to the crank wheel. Again, the origin is the axis system that I've placed there, and the direction is actually placed from the axis of the crank, and the direction of rotation depends on which way that arrow is placed there. So you can change the direction of that and it will actually turn it, but there should be a symbol which indicates the direction that that's going, but for some reason or other on the graphics I can't get that to show. I must be doing something wrong. And I've worked out that an average rider could possibly put about 150 newtons at 120 millimeters, so the torque there works out to about 18 newton meters. Again, the science you can actually discover for yourself. And those two extras in terms of the excitations are actually the rider and the power that are placed in there, and that's been simulated. So if I take the heavy rider out, let's see what that actually does to the simulation. It'll probably make the bike go actually unstable, but let's have a look, see what it does. And you can see that without a rider on, the torque is actually whizzing the bike off the track. So we need to put the rider back in to make sure that it loads the spring properly, and hopefully that will simulate. Okay, back to where we were. Yeah, so that makes a difference. The next thing is, what I want to do, I want to measure how much this spring deforms under the inertia and the load of the rider as it's moved along. And if we just look at that simulation and see if we can watch this minimum distance value, we should see it changing as the bike rolls around. And I'll just let it roll off the end of here, and we'll just see what that value goes to as it bounces off the cliff. Not difficult to see as it's moving, but what I did was I added some probes in there, and there's two. The first one is measuring the all the probes are in here: measure probe, position, speed and acceleration, joint force, sections, interference, and even a camera probe. So what I did with this one, I put a measure between, and I simply selected the points on the top and the bottom of the damper, so I could see what that distance was changing to as it went down the track. The second one is the position, speed and acceleration. So the point I'm interested in is where that point, that axis system of this frame, as you can see we've got the frame as a reference product, and the position axis is the absolute axis, which is the axis of this vehicle, and then we should be able to compute the distance it travels, and other things, position, speed and acceleration of the bike as it moves down the track. So they're the probes that are in place, and in the scenario we can see a second tab where I've put that measure and position probe to be referenced in this particular scenario. So I won't do it now, because if you go into there and do that computation, oh no, let's do it. It will actually compute, and as it computes, it actually runs the simulation until it's actually done that computation, and that should update this set of results that I've previously done. I think it will take a few minutes to go over. Obviously it's running for more, well, for that 2.5 seconds, which will actually drop the vehicle over the end of the track. But I suppose what you can do, because it's going slow, because it's computing things, we can actually see what's happening to that damper, and away it goes off the edge of the track, and that is computed. Now when it's done that, it actually drops into the results window and it provides us with a different tab, and we can play that animation, or in fact we can look at the plots that it's created in here. Now it produces quite a lot of information, and if we look at the plots, they're extremely busy. So what I was particularly interested in, if we deselect all these, I was interested in the measure of the damper, and you can see this plot here is measuring what happens at 2 seconds or so. We've got to about 52 millimeters. This will be the position where it's dropping off the end of that that ramp. So that's about 58 millimeters there. And the second thing I'm interested in really is the position, but you can see that you've got angular acceleration, you've got a linear acceleration, linear velocity, but I'm also interested in the position. Let's just tick that one. That's bound to be 0. Where is it? Linear velocity and magnitude. So you can see the changes in velocity as it's running off and as it whizzes over into space here. The linear acceleration, we can see that changing with time, and angular velocity, angular acceleration, and also the positions of various commands that are actually in the thing there. So you do get quite a lot of information. Let's see what happens with this rider force. Stays pretty constant at the 900 newtons all the way through. So there we have it. That is what we have got in our little simulation there. Hopefully you'll find that interesting. There's a lot more information in terms of what we can actually get out of this, but to move it back from the results window, we just simply double click on the scenario we're interested in, and it will move the actions pad, the commands tabs back to Mechanical Systems Experience, but looking at the scenarios. So there's all sorts of things that we can do here, which are beyond my ability to show you in this video, that we can look at. So which is quite interesting. So in terms of the results, if I click in the results page again, we can actually look at a geometric trace or a sweat volume. So we could do a geometric, no, let's try a sweat volume. It needs to have a shape that it puts that in. We can OK that, and we can look at removing these. So it's going to sweep the shape of this, but we could actually deselect some of these. So let's just look at, let's just deselect all that. So we can just look at where the frame goes to, and OK that. And it actually creates a shape here, which should be in space somewhere. There it is. So as the bicycle sweeps along its track, that's the shape of the swept volume of that particular thing. So I can dump that because it keeps that shape actually inside the results window, and if you want to have a look at it again, we can actually open the representation and it will open it up here. Let's tick that up and just do a view. I'll zoom all in. There we go. So I hope you found that useful, and you know, if anybody's got any tips, then let me know. Okay, thank you very much.